Tonight, we are going to look at the darkest thing there is, slowly, and take the fear out of it. A black hole is not a hole. It is not an opening, not a tunnel, not a drain, and not a thing made of any material. Nothing has been taken out of space to make one. If anything, there is more there than anywhere else. It is easier to say what one actually is. Take some amount of matter and press it into a small enough space, and the gravity around it becomes strong enough that nothing which leaves the surface can get away, including light. At that point, the matter itself stops mattering. What is left is a region of space with a particular shape and a boundary, and almost no other properties at all. How stars end, and which of them collapse, was the last episode on this channel. Tonight we start with one that already exists and work from the edge inwards, and then back out to the strange fact that we have photographed two of them. 14 things. And nothing here requires you to be awake. If you fall asleep before the end, that is fine. A black hole is not made of anything. A star is made of gas. A planet is made of rock and metal. A black hole is not made of a substance in that way at all. Whatever fell in to make one has gone somewhere we cannot describe, and what is left behind, outside, is pure shape, curved space, and a boundary. If you weighed everything that a black hole is, from the outside, you would get one number, its mass, and that number tells you nothing about what it was made from. This is worth sitting with. Two black holes of the same mass, one made from collapsed hydrogen, and one made in principle from a mountain of iron, or from light, or from books, are not merely similar. They are identical. There is no measurement anyone can perform on the outside that distinguishes them. Nothing else in nature is like this. Every other object carries its history in it. A rock says what it was made of. A star's light carries the elements in its outer layers. A black hole has no surface, no composition, no color, no temperature you could measure in any ordinary way, and no memory that we can read. It is the simplest object known, and it is made of geometry. The edge is not a surface, and there is nothing there. The boundary is called the event horizon, and the word horizon is exact. It is not a wall, it is not a membrane, it is a place where the accounting changes. At every point in space, there is a speed you would need to leave and never come back. On Earth, it is about 11 kilometers a second. Closer to a heavy object, it is higher. The horizon is simply the surface where that speed reaches the speed of light. Inside it, leaving is not difficult, it is not available, nothing marks it. There is no material there, no glow, no barrier. If the black hole is a large one, you could cross the horizon without noticing anything at all. The space around you would look ordinary. You would not feel a boundary, because a boundary is not a thing you feel. It is a statement about which futures still exist. The size is set by the mass and nothing else. For a black hole, the mass of the sun, the horizon is about 3 kilometers across the radius. For one, the mass of the Earth, it is 9 millimeters. It is worth noticing what this means. The horizon is not the object. It is the distance at which the object stops being able to send you anything. We name black holes by the size of their silence. Anything can become one, and almost nothing does. There is no special material required. Any mass, compressed enough, becomes a black hole. That is a statement about gravity, not about exotic matter. The sun would need to be squeezed to a ball about 6 kilometers across, The Earth would need to be squeezed to the size of a small marble. Your own body would need to be compressed to a size far smaller than a single atomic nucleus, smaller than anything can be compressed to by any process we know. So the requirement is not weight, it is concentration. And nothing in the universe supplies that concentration except gravity itself, working on something already very heavy. That is the reason black holes come in the sizes they do and not in others. There is one more consequence which surprises people. Very large black holes are not dense at all. Because the horizon grows in proportion to the mass, but volume grows as the cube of it, the biggest ones have an average density lower than water. There are black holes at the centers of galaxies whose average density is thinner than the air in this room. A big black hole is not a heavy small thing. It is a very large region with a great deal in it, spread thin. Nothing is pulled in that was not already falling. The common picture is of something that sucks. It does not. Gravity from a black hole obeys exactly the same rule as gravity from anything else of the same mass. There is no extra attraction and no reaching out. The clearest way to say this is with a swap. If the sun were replaced this instant by a black hole of exactly the same mass, the Earth's orbit would not change in any way. Same period, same distance, same year. It would grow very cold and very dark, and that is all. There is no pull towards the black hole that was not already there. The strong effects are all close in. Gravity gets extreme near the horizon because you can get so near to so much mass, not because the mass is greedy. At the distance of a planet, a black hole is just a mass. Real black holes do swallow gas, and a great deal of it. But that gas has to lose its orbital motion first, by rubbing against other gas before it can fall. Material in a clean orbit stays in orbit indefinitely, as it would around a star. The galaxy is full of things quietly circling black holes and not falling in. The bigger one is the gentler one. Gravity pulls harder on the near side of an object than the far side. That difference is what makes tides on Earth, and near a small black hole it is severe. The difference between your feet and your head could be large enough to matter long before you arrived. The surprising part is that this gets weaker as black holes get bigger. For a black hole of a few solar masses, the horizon is a few kilometers across, and the change in gravity across a human body near it is enormous. For one of several million solar masses, the horizon is bigger than the Sun, and the gravity a meter apart is nearly identical. You could cross the horizon of a very large black hole and feel nothing unusual at that moment. That is the strange asymmetry of these objects. The small ones are violent at the edge, the large ones are calm at the edge, and everything difficult happens much later and much further in a region nobody can describe. The most dangerous black holes to approach are the least impressive ones. A black hole has only 3 numbers. Every object you have ever seen requires an enormous amount of information to describe. Shape, temperature, chemistry, texture, rotation, history. A black hole, as far as anyone can measure from outside, needs 3 numbers. Its mass, its spin, its electric charge. That is the whole description. 2 black holes with the same 3 numbers are the same object in every respect. This result came out of general relativity in the 1960s and 70s, and it is usually stated as a short sentence. A black hole has no hair. The hair means detail, and there is none. In practice, it is closer to 2 numbers. Charge does not survive in the real universe because the universe is full of loose charged particles, and any black hole with a strong charge attracts the opposite kind until it is neutral again. So, mass and spin. The mass tells you the size of the horizon. The spin tells you how much space near it is being dragged around. Nothing else about the object, and nothing at all about what it ate, is available. This is why the question of what happens to the information that fell in has occupied physicists for 50 years, and why there is still no agreement on the answer. That disagreement is real, and it is unresolved, and anyone who tells you otherwise is choosing a side. Time at the edge does two different things. Gravity slows clocks. This is measured ordinarily on Earth. A clock at the foot of a mountain runs slower than one at the top, by an amount now detectable over a height difference of a few centimeters. Near a black hole, the effect becomes total, and it produces a description that sounds contradictory but is not. Watch a clock falling towards a black hole. From your distance, it ticks slower and slower as it approaches the horizon. It never quite arrives. Its light gets redder and dimmer and slower and fades away, and in the arithmetic, it takes infinite time to reach the boundary. Now ride with the clock. It ticks normally the whole way, as clocks always do where they are. It reaches the horizon in a perfectly ordinary and finite number of seconds and crosses. Both accounts are correct. They are not two opinions about one event. They are two different measurements, made along two different paths through time, and relativity says there is no third, truer view that settles it. This is the thing that is hardest to hold on to about black holes. Not the darkness. The fact that the question, when did it cross, does not have one answer. They spin, and they drag space around with them. Stars rotate. When a star collapses, that rotation has nowhere to go, and the smaller the object gets, the faster it turns. Black holes formed this way spin, and many spin very near the maximum the theory allows. A spinning mass does something to space that has no everyday equivalent. It drags it. This is called frame dragging, and it is not a metaphor. Space itself is carried around, so that near a spinning black hole, nothing can stand still. Not because of a force, but because standing still relative to the distant stars is no longer one of the available options. This has been measured, weekly, near the Earth, which also drags space around itself by a very small amount. Satellites carrying precision gyroscopes have detected it. Around a black hole it is extreme, and it is useful. The energy stored in the spin can be extracted by magnetic fields threading the region, and this is currently the best explanation for the jets. Narrow beams of matter thrown out from the centers of some galaxies, straight, for distances larger than the galaxy itself. The brightest and most violent things in the universe are powered by the rotation of something that emits nothing. The brightest objects in the universe are made of things falling. A black hole gives out nothing. The neighborhood of a black hole can be the most luminous thing there is. Both are true at once, and the second is how we find them. Gas that gets close does not fall straight in. It goes into orbit and forms a flat disk, and the inner parts of that disk travel faster than the outer parts, so the layers rub. That friction heats the gas to millions of degrees, and hot gas shines. The efficiency is what makes this remarkable. Nuclear fusion, which powers every star, converts about 0.7% of mass into energy. Matter falling towards a black hole can release something like 10%, and for a rapidly spinning one, more. It is the most efficient way of turning matter into light that exists in nature. This is what a quasar is. A single black hole at the center of a young galaxy, being fed, outshining every one of the hundreds of billions of stars around it, from a region no larger than our solar system. The darkest object in physics is the reason for the brightest light in the sky. The picture is not of the black hole. In 2019, a photograph was released of the object at the center of the galaxy M87, and in 2022, of the one at the center of our own. Both were made by linking radio telescopes across the whole Earth, so that they worked as a single instrument the size of the planet. It is worth being exact about what is in those images, because it is not the black hole. Nothing can be. What is shown is a bright ring with a dark patch inside it. The bright ring is light from hot gas, some of it from behind the black hole, bent around it and delivered to us, which is why the ring closes into a circle from any viewing angle. The dark patch is the shadow, the region from which no light can reach us at all. The shadow is larger than the horizon, by about half again, because light that passes near the horizon is bent inwards and captured even though it never crossed the boundary. So the image is a silhouette in light that came from behind and around. We have photographed the absence, outlined by everything it is standing in front of. There is one in the middle of this galaxy, and we found it by watching stars. At the center of the Milky Way, about 26,000 light-years away, there is an object of about 4 million solar masses. It is called Sagittarius A star, and the way it was established is one of the most patient measurements in science. Two teams watched a small cluster of stars near the galactic center in infrared light because dust blocks the visible, and they did this for nearly 30 years. Long enough to see the stars move, long enough to see them curve, long enough to watch one of them, called S2, complete an entire orbit, which takes about 16 years. An orbit gives you the mass inside it, 4 million suns. And the orbit comes in very close, which means all 4 million are packed inside a region smaller than our solar system. Nothing else can be that heavy and that small and that dark. The work was recognized with a share of the Nobel Prize in Physics in 2020, and the object was photographed 2 years later. We knew what was there by watching a few faint stars go around it, slowly, for 3 decades. Every large galaxy has one, and nobody knows why they match. Once astronomers could weigh these objects, they weighed them everywhere and found that essentially every large galaxy has one at its center. Then came the part that is genuinely unexplained. The mass of the central black hole tracks the properties of the galaxy around it. In particular, it tracks how fast the stars in the central bulge are moving. Faster stars, heavier black hole, and the relationship is tight, over a range of masses spanning a factor of 1,000. This should not be obvious. The black hole is minuscule compared with its galaxy, about 1 part in 1,000 of the bulge's mass, and its gravity dominates only a tiny region at the center. The stars in the outer galaxy do not feel it at all. They are held by everything else. Yet the two grew together. The favored explanation is that the black hole regulates its own growth. When it feeds hard, it heats and blows out the gas around it, which stops both its own feeding and the formation of new stars. That is plausible, it is supported, and it is not settled. A small dark object at the center of a galaxy appears to know how big the galaxy is. Two of them colliding make a sound in space itself. When two black holes orbit each other, they lose energy, not as light, which they cannot emit, but as ripples in the shape of space, spreading outwards at the speed of light. As they lose energy, They spiral closer, and as they get closer, they orbit faster, and the ripples get stronger. At the end, the last orbits take a fraction of a second, and the two merge into one. On the 14th of September 2015, two detectors in the United States, each with arms 4 kilometers long, registered a passing ripple from two black holes of about 30 solar masses each, merging somewhere over 1 billion light-years away. The size of the effect is worth stating plainly. The detectors measured a change in length of about 1 part in 10 to the power of 21, a fraction of the width of a proton, over 4 kilometers. The event converted about 3 solar masses into pure gravitational waves in under a second. For that instant, the power radiated exceeded the light of every star in the observable universe combined, and none of it was light. Well over 100 such events have been recorded since. They arrive, on average, every few days. They leak very slowly, and nobody has seen it. In 1974, Stephen Hawking showed that black holes should not be completely black. Quantum theory applied near the horizon predicts a faint thermal glow, and it means a black hole slowly loses mass and, in the end, disappears. 3 things about it are worth keeping straight. It has never been observed. Not once. It is a prediction from combining 2 theories that we have never confirmed at this boundary, and it should be described as a prediction. The rate is unimaginably slow, and it works backwards from what you might expect. The bigger the black hole, the colder it is. A black hole of a few solar masses has a temperature of about 100 billionth of a degree above absolute zero, far colder than the cosmic background radiation that fills all of space. That means it absorbs more than it emits. It grows. Nothing in the universe can evaporate yet, and nothing will until the background cools in something like 10 to the power of 100 years. And the final state is unresolved. If a black hole evaporates completely, what happened to everything that fell in, and to the information it carried? Quantum theory says information cannot be destroyed. The straightforward reading of relativity says it is gone. 50 years of work has not produced agreement, and this is the honest position. It is an open problem, not a settled story. The last black holes will still be here long after the last star, quietly holding their 3 numbers. That is 14 of them. There is a pattern here that is different from the other episodes on this channel. Usually, the more closely you look at something, the more detail appears. With these, it goes the other way. You look closer and there is less. No surface, no material, no color, no history, no chemistry. Just mass, spin, and a boundary, whose only property is that things do not come back. Most of what we know about them, we learned indirectly, by watching a few stars move for 30 years, by measuring a length change smaller than a proton, by linking telescopes across a planet to photograph a shadow in light that came from behind. And there is a great deal we do not know, which this channel prefers to say out loud. What happens at the center is not described by any theory we trust. What happens to the information is not agreed. The connection between these objects and the galaxies around them is measured but not explained. There are millions of them in this galaxy alone. Almost all are quiet, taking in nothing, orbiting the center with everything else, giving off nothing at all. They are the calmest objects there are. Sleep well.